Hello everyone, welcome to my class. Today I am going to cover a surface integral, which is also called the flux. First, quick note, we do not cover parametric surfaces. So first let's start with the notations. We denote the surface by z equals to function of gxy. We reserve the lowercase f for scalar field. There are two types of surface. One, orientable, which has two distinct sides. Another one is non-orientable. The example for non-orientable surface is Mobius stripe, band, which has only one side. Now let's go to the orientable side. The example is spheres, cones, cylinders, planes, etc. Positive orientation means the normal vector points upward. So for example here it's pointing upward. And negative orientation means the normal vector points downward. For example here. Okay, so let me scroll down. We know this quick recall here. Area of surface is denoted by AS and is defined as double integrals of the radical 1 plus gx square plus gy square times dA, and integration is over d. So little bit of surface is ds equals to under the root 1 plus gx square plus gy square dA. We know normal vector is n equals to the vector negative gx, negative gy, 1, and this 1 is a z component, which is positive, means our normal vector is points upward. If this 1 is negative, that means the normal vector points downward. And also we know vector surface element ds equals to nds or nda. Now let's talk about surface integral. Let me scroll down. There are two types of surface integral we study. One, the surface integral of scalar field, and another one, the surface integral of vector field, which is also called a flux. So let's talk about first one, A, the surface integral of scalar functions fxyz over the surface S is denoted and defined as double integrals of f over the surface S equals to double integrals of f of xy, this is same as z equals to function of xy, times under the radical 1 plus gx square plus gy square dA, and we integrate over the two dimensions domain, which is the projection of surface on xy plane. Quick note, if our little f is constant 1, then the surface integral becomes the surface area. That is, double integrals of f, which is 1, ds equals to double integrals over d, this is 1. So 1 plus gx square plus gy square dA is simply area of the surface. Next, let's define this flux. Suppose the velocity of a fluid in the space is described by the vector field f, and s is the surface, then the flux of f across the surface is the total amount of fluid crossing the surface per unit of time. Let's move on. Another definitions. Definitions B. The surface integral of a vector field f, whose component are p, q, r, over the positively oriented surface S with a normal vector n is given as follows, is normal surface integrals or surface integral of f over the surface S equals to all the way here. So double integrals over d of negative p times gx minus q times gy plus r times dA. This is the formula. Now we are ready to do the example. Let's do example. Let's compute the surface integral. First example, evaluate the surface integrals of x square yz over the surface S, where S is the part of the plane. The plane is given by z equals to 1 plus 2x plus 3y that lies above the rectangle 0, 3 cross 0, 2. So the bounds of our plane region D is given by here. X is between 0, 3, y between 0, 2, and then the surface is z equals to 1 plus 2x plus 3y. So we take a partial derivative of this g and apply the formula. Great. So let's start the solution. Z equals to 1 plus 2x plus 3y. Take the partial derivative of z with respect to x, which is 2. Take partial derivative of z with respect to y, which is 3. Hence, given surface integrals of x square yz over the surface equals to, by formula, double integrals over d, x square y, replace z by 1 plus 2x plus 3y, and then under the radical, gx square 2 square plus zy square 3 square plus 1 times dA. Let me scroll down. That's better. So here the dA is in our descriptions dy dx with the y limits and with the x limit. First evaluate this, simplify this under the radical, which is 4 plus 9 plus 1 14. So pull the radical 14 outside, and the double integrals. So inner integral is y integrals for dy, outer integral is x integrals for dx. So inside, let's FOIL this one, x square y times 1, x square y times 2x, x square y times 3y, here 3x square y square times dy dx. Integrate first with respect to y. Keep in mind your x terms are constant. So next step, radical 14 as it is, write down x integral. Integration of x square y with respect to dy is x square y square over 2. Integration of 2x cubed y with respect to dy is x cubed y square plus integration of x square y square, and then times 3 is x square y cubed, because y square becomes y cubed over 3 and 3 cancel. Put y limit times dx. The next step, radical 14 as it is, integration of x as it is. You simplify, put y equals to upper limit 2 and simplify. This gives you this x integrals. Then integrate with respect to x. Then put x limit 0 to 3 and simplify. This gives you 171 times radical 14. This is the surface integrals value given in example 1. Great. So now let's move on. Now let's compute example 2. Example 2 says evaluate the flux or the surface integrals of vector field f over the surface S, where vector field is given f equals to xy for x square yz, and surface is z equals to x times e to the y, where x bound 0 to 1, y bound 0 to 1 with upward orientations. So great. So now our the function that we are taking derivative is the surface. So z equals to x ey. Take the partial derivatives. So z with respect to x is simply ey. Ey is constant for x derivatives, and partial derivative z with respect to y is x ey. X is constant, ey becomes itself ey. Then the flux for the given surface integrals after ds over s equals to, by formula, double integrals over d of negative p gx minus q gy plus r times dx. Then the double integrals, the dA is dy dx, so double integral is over x and y with x and y bounds coming from here, and then negative p, which is negative xy times gx is e to the y, minus q is 4x square times gy is x times e to the y, plus r is yz times dy dx. Great, let me scroll down. So then in the next step, we are integrating over y and x, so let's first replace your z in terms of x and y, which is given here. Z equals to function of x and y, which is x ey. So put z equals to x ey, and then this one and these terms cancel out. Okay, so then the next step, -4 as it is, we pull outside, x integral as it is, y integral as it is, then x cubed ey, which is here, dy dx. Then I think it's better, let me go down here. Then here, then integrate first with respect to y, so write down -4 as it is, x integral as it is, x cubed e to the y becomes x cubed e to the y, because in y integrations x cubed is constant and ey doesn't change with respect to y. Same here. You put y limit times dx, -4 x integrals, put y equals to 1 and y equals to 0 and simplify, which gives you x cubed e minus x cubed times dx, and take integral with respect to x, so -4, this e as it is, x to the power third becomes x to the power 4 over 4, 4 cancelled, so this term is here, x to the power 4e minus x to the 4 over 4, this 4 and this 4 cancel again, x to the 4, put x equals 0 to 1, then simplify, it gives you 1 minus e. Great. Let's continue. Example 3. Find the flux of vector field F whose components are xy, yz, zx across the surface S, where surface is the part of the paraboloid that lies above the square and has upward orientations. Great. So let's start. So the functions, we are taking the partial derivative is the surface, which is z equals to 4 minus x square minus y square, and take the partial derivative of z with respect to x, which is -2x. Partial derivative of z with respect to y is -2y, and then use the formula. So the flux equals to Dahal integrals over d of -p gx minus -q gy plus r times dA. And our domain is this square here, where x ranges from 0 to 1, y ranges from 0 to 1. So the x limit and y limit, -p, -xy times this partial derivative, -q, -yz times this partial derivative, -y, plus r is gx times dy dx. Next, let's replace z is given equations here, which is 4 minus x square minus y square. Next step, let me scroll down. Next step, write down x integrals, write down y integrals, and then put z equals to 4 minus x square minus y square, and multiply here, multiply there, and then simplify. This gives you this expressions times dy dx. Then next step, write down the x integrals, integrate first with respect to y, but keep in mind your x terms are constant for y integrals, which gives you this long expressions, and put y limit y equals 0 to 1 times dx. Then in the last line, put y equals to upper limit minus lower limit and simplify. This gives you this x integral, just routine computations. Then integrate x with respect to x, these terms, then this gives you this expression here. Put x equals to 0 to 1, then simplify. So this gives you the final answer is 713 over 180. Awesome. So great. So we finished the sections. So just a heads up, in next lecture we will study divergence theorem. Thank you.